Assuming you know about relations, let's talk about what kind of properties they can have. For simplicity, we will use R that are a subset of A times A, so the input and output set are the same, and we will use the transition-based representation of every relation. So there are three main families of properties. One is reflexivity. We will call a relation reflexive if for all members of the base set XX is in a relation. So you can go from any element to itself. A typical example of a reflexive relation is equality, which basically is the most primitive reflexive relation ever. It just does everything that's expected from reflexivity, but nothing else. Equivalence usually does some more stuff, but does not have to. And basically any non-strict relation that allows stuff to be equivalent, that is reflexive. So greater than or equal, lesser than or equal, non-strict subset, and whatnot. Then we also have an irreflexive relation, which is different from simply not being reflexive. If you are not being reflexive, it means you do not satisfy the conditions for reflexivity. Irreflexivity means that you have the opposite situation. So for all members of a set, the relation of a member of an element to itself is disallowed. So these these idle cycles from an element to itself are not allowed. So any strict comparison is irreflexive, and basically any kind of relation where we cannot think of anything idle or anything with which results in the same elements. We also have a co-reflexive relation, which is a kind of thing that says that we can have reflexive parts, but we don't have to have all of them, but we should not have any irreflexive parts. So if we have a relation from x to y, then x is the same as y. So it basically means that empty relation, for example, is co-reflexive. Otherwise, if our base set is not empty as well, then it is not reflexive, because the smallest reflexive one is equality. So talking about smallest ones, there is this thing called reflexive closure. It is a reflexive closure of a particular set. So if we have a set, of a particular relation. So if we have a relation R, then a reflexive closure of R contains R, but also is reflexive, and it's the smallest one of those possible. So we want to add as few things as possible in order to have a reflexive relation. Examples: if we have equality, it's already reflexive, so closure remains the same. If we have a strict relation, then its closure is its non-strict variant. So from less than we get less than or equal. From greater than we get greater than or equal. Suc is basically the next integer relation, which goes from 1 to 2, from 2 to 3, from 3 to 4, and so forth. So its reflexive closure is self or suc. So from 1 you would go to not only to 2, but also to 1 itself. If you have a base class relation, so subclass or superclass, then its reflexive closure would be itself or your inheritor, or your subclass or your superclass. And if you have an empty relation, not an empty base set, but an empty relation, then its reflexive closure is just equality. The second big family of properties is transitivity. So we call a relation transitive if we can go from any element to another element and then to another element, then we can also go to that third element directly. So if something is reachable by some means, then it should also be reachable in one step. So yes, it looks like this, and everything is reachable from everywhere in this particular example, but it doesn't have to be. So anything that is reachable should be also reachable in one step. That's the most important part. And again, if we talk about not just reachability, but inheritance, for example, then transitive relation is something that talks about inheritance in general. So is this class eventually in the class hierarchy below us, or is it eventually somewhere among our ancestors, versus direct subclassing. We also have a non-transitive relation, which is if we can go somewhere in 2 steps, we should not be able to go there with 1 step. And since we can apply the same formula over and over, it means that if something is reachable, and there is only one way to reach it. Transitive closure is defined the same way as a reflexive closure, so it is a smallest relation that includes the original and is transitive. So in this particular case, we need to edit quite many arrows, but suppose we didn't have this one, it means we also do not have that one. So in this case, the element number 3 is reachable from 2, and 2 is reachable from 1, which means 3 should be also reachable from 1. But 2 is not reachable from 3, so we don't care about that. Transitive closure example, so if we have equality, it's already transitive, so fine. If we have smaller than, it's also transitive, so we are fine. If we have a successor, its transitive closure is actually smaller than, because if we can link 1 to 2 and 2 to 3, which means 1 and 3 should be there, but then we have 1, 3 and 3, 4, which means 1, 4 should be there, and so forth. So basically you end up adding all possible numbers, which is the smaller than relation. Baseless is then generalized to transitivity, to inheritance. We talked about that. And if we have an empty relation, then it just remains empty, because if nothing is reachable, then nothing is reachable in 1 step. Perfect. The third family is symmetry. So we call a relation symmetric if for all elements, if we can go from x to y, we should also be able to go from y to x. Very straightforward. So basically each step, if we think of a relation in terms of transition system, each step is undoable. If we can go somewhere, we can also return in 1 step. Then we have an asymmetric relation, which means that if we go somewhere, we can not go back in 1 step. And that's direct opposite. So it kind of contains irreflexivity, which is slightly annoying, because then you are not allowed to have this little idle loops for elements. So for this case, there is an antisymmetry relation, which is slightly weaker, which says that if we can go from x to y and from y to x, it means x and y are just the same thing. So antisymmetry basically means that we are kind of not really symmetric, but we can be reflexive. So non-idle steps are not undoable, but idle steps, they're still allowed. And then we have symmetric closure, which is defined the same way. It basically contains the original relation, it's very small, and it is symmetric. So what do we have if we add these things up? If we have proper reflexivity, transitivity, and symmetry, we have equivalence. And this is a very important property, a very important relation. So this gentleman on the right, called Stephen Kleine, an English mathematician who introduced us to regular expressions. He also talked about closures for the first time. And you will see mostly the transitive and reflexive transitive closures, but there could be a reflexive closure. Symmetric closure is less useful, but still exists. But reflexive and transitive and symmetric closure also exists, and is basically the smallest possible equivalence relation built upon this R thing. But basically what it means, so R, the reflexive closure of R is also denoted as R0, which is kind of to the power of 0, which means we take a relation and we take 0 steps. So taking their 0 steps means that we stay where we are, which is precisely reflexivity. So this is 0 steps. Transitivity means 1 or more steps, any number. Reflexive and transitive means a combination of the above, so it is 0 or more steps, and this is 0 or more steps with the possibility to go back at any time. Summary is that we have introduced reflexivity with variations, transitivity with variations, and symmetry with variations. All of them combined are called equivalence, and we also have closures, which are extensions to existing relations which satisfy these properties. That's it. Thank you.